All right, so we got to take a few notes about colligative properties, and here's why. Actually, there's a couple reasons. The primary reason is that the calculation of molality we're looking at right now is primarily used for calculations involving colligative properties. Okay. The other thing is there's something about the tactile stimulation of taking notes that helps you remember things. Okay. So why don't I just give you the copy on a piece of paper and ask you to read it? Reading is not as an effective way of remembering things as it is to copy it down. But they're both better than not doing anything, just listening. Okay, so what you really need to do is listen, read, take notes, and go back and review. All right, colligative properties. Let's first define what that means. These properties are those properties that, well, I can't spell properties. Those properties of solutions, since we're talking about solutions, that result from the number of solute particles. That word particles is very important. We'll get back to defining that a little bit later. The number of solute particles per constant amount of solvent. These properties do not have to do with the way solute particles interact with solvent particles. Interact, yeah. You could say attract to or repulse. So that kind of interaction. Pushing away or pulling toward. It's a lot like the kinetic molecular theory we studied in Unit 7, the previous unit, where we said in the kinetic molecular theory we could do some simpler math with the ideal gas equation and Charles' law, Boyle's law, things like that, if we ignore the attractions between gas particles. That's kind of what we're doing here. We're not looking at the attraction between these solvent and solute particles. We're just looking at the effects of having a certain number of particles in solution. But particles is a key thing to remember, because particles in this case doesn't mean a formula unit. It doesn't necessarily mean a molecule or an atom. It means something else, and it goes back to Unit 5 when we're writing complete and net ionic equations. All right, the types of colligative properties we're going to learn about in this unit are freezing and melting temperature, the types of colligative properties. The temperature at which a substance freezes is the same temperature at which that substance melts. The temperature at which something freezes is the same temperature at which that substance will melt. Water freezes at 0 degrees C. Water also melts at 0 degrees C. What?
Oh, so 0 degrees C is actually 33 degrees?
Yeah, Fahrenheit is 32 degrees. That's right. Okay, boiling and condensation temperature are also the same. Water boils at 100 degrees C. Water also condenses from gas to liquid at 100 degrees C. That's about 212 degrees Fahrenheit. That's correct.
Yeah.
All right, and the third type of colligative property we need to know about is vapor pressure. And for a firefighter, vapor pressure is especially important. Because understanding vapor pressure is critical to understanding when you're likely to get a fuel into the gas state where it can burn. Okay, now, we're not going to do any math with vapor pressure. The categories or types of colligative properties for which we are going to be doing math, and the reason we learned about molarity a minute ago, or a little earlier, is that we're going to be doing calculations with freezing and melting temperature. But not so much the temperature itself as it is the change. I mean, there's a little bit of both. And the boiling condensation temperature change, freezing melting temperature change. I'm sorry, boiling and condensation temperature change. Yeah. Turns out that these two properties are calculated with the same set of equations. Okay? We just have to plug in some different values into those equations. So the equations we're going to be using, and there are two of them you need to know for both freezing and melting temperature and for boiling condensation temperature. Equations. Okay? For both of those, you got, it's called delta T. The triangle is the Greek letter delta, capital Greek letter delta. That's a small letter I, capital letter M, small letter M.
Small letter I.
Capital K, small letter M.
That time.
Yeah, these are time signs. That's correct. Now then, since you've got freezing melting temperature and boiling condensation temperature, this gets modified slightly for one of those two categories. For the freezing melting temperature, it's the change in the temperature of freezing equals this I times this constant for freezing times M. Yeah, that's for freezing. So this is the one that's used for freezing and melting temperature change. And then the same sort of thing is done for the boiling condensation temperature. It's change in the temperature of boiling equals I and K sub B for the constant for boiling.
That's KF.
That's KF there. And M. So this is the one we use for boiling and condensation over here. Oh, I promise you won't die. You already finished all that? I'm talking to Chandler. Okay. Here. And then the second equation you got to be able to do or work with is also starts with delta T, but this is one where we have what's called the final temperature minus the initial temperature. So let's define what all these symbols mean, what the terms mean. Okay. Delta T means change in temperature. And just so that you know, delta, the Greek letter delta, is used in this context to mean change. And you know from the last unit that the capital letter T we use for the symbol for temperature. Small letter I. This is something that has a name called the Van't, that's a small letter V, Van't Hoff, capital letter F, Van't Hoff factor. The guy who came up with this, I guess.
If he came to, what's his name? His last name,
I don't know. He might be kin to Van Helsing. I don't know.
no, you know who he hoped? No, dude. Got Talent. America's Got Talent? Yeah.
Well, I don't know. I don't watch that show. Okay.
Hasselhoff.
Oh. All right. No, it's not that Hoff. Okay. The Van Hoff factor. The Van Hoff factor. Listen. Is the number of particles. Remember I told you to remember that term from earlier? The number of particles. The number of particles a solute splits into when dissolved in a solvent. The number of particles a solute splits into when dissolved in a solvent.
One little letter name.
Yep. Okay, so if you're struggling with this concept when we get to it at all, you need to go back to Unit 4 text and review complete ionic equations. In fact, you could go back to Unit 3 and 4 where we learned to first write formulas, and we just did one for calcium chloride a moment ago. Unit 5 is where we wrote the complete ionic equations. Unit 3 and 4 is where we first started writing the formulas, and then when we went to get to 5, we undo the formulas to write the complete ionic equations. Okay? K.
Potassium?
Well, in this case, this is a constant. This K means a constant. And it's either the freezing point constant which we symbolize as K sub F, or boiling point constant, which we symbolize K sub B. Then we're going to have the small letter m. That's what we spent the first part of the class learning how to do, calculating m. This is the molal concentration. You can call it molality. And that's the mole concentration of the solution. T subscript F, capital F here, is the final temperature. That's what we call it, final temperature. This does molal concentration. And T subscript capital I, initial temperature. Okay, T sub I, the initial temperature, in this context, is always the freezing or boiling temperature, depending on which one we're working with, of the pure solvent. Okay, let's do another class problem here. I'm going to help you. I'm going to walk you through this one, and then you'll be able to do the homework problem I gave you earlier. So at 5.93 grams of calcium chloride is dissolved in 1,000 grams of water, what is the freezing temperature of the solution? Okay. Well, we already calculated the molality, and I did that for a reason. Okay, this is the one we already calculated the molality for. So we already know what M is here for this problem. M for this problem only, we already calculated to be 0.0534. And this is from the earlier problem we did. Okay. Now, you're going to need your text to find K sub F. We need the freezing point constant, and this is in your text. Please get out your Unit 8 text. KF. So on page 340 of your text, table number 2 has a list of freezing point and boiling point constants along with freezing and boiling temperatures. 340. I will have to give you this. I'm not going to make you memorize it, okay? All right. We're looking what's going to happen to water here. Water is the solvent, okay? So what's the change is from the change in the temperature of the pure solvent. So we're looking at water here for the KF. The freezing point constant for water is a negative 1.86. And remember, we always put in the in the column labels, we put the units of measurement. We don't put them in the cells. So the units we're going to write with this number are degrees C per mole. Okay? So it's negative 1.86 degrees C per mole, which we probably should write in our problem as negative 1.86 degrees C over mole. That means the same thing. Mole. All right? I. Okay, we wrote the formula for calcium chloride earlier. We figured out that there was one calcium particle and 2 chlorine particles. 1 calcium ion and 2 chloride ions. That's a total of 3 particles. So I here is 3, just the number 3. It's a counting number, doesn't need any units. Okay? So we're at least ready to put this into this equation. Delta T for freezing is equal to I times K sub F times molarity, or molality rather, mole concentration. So I is 3, K sub F is negative 1.86 degrees C over mole concentration. And the mole concentration is 0.0534 mole. And to make all this work out so we can see what we're going to cancel easier, let's put these last two, or this first one and that last one over 1. Okay? So we plugged in I. There's 3. We plugged in K sub F. There it is right there. We plugged in the mole concentration right there. Then you cancel out mole concentration. We're left with a degree C, which measures temperature, and we're looking for a change in temperature here. So this is a negative 0.297972. Now you've only got a few more minutes. Degrees C. Hello? That's it? Sure. Mac, when you leave here, you go by attendance. Okay, Matt. All right. So we're going to, we only need 3 significant digits. This is a counting number. We don't use counting numbers for figuring out significant digits. This is a multiplication division problem. This has the least digits. 3 digits, rounded off. Yeah, here's the number right here. And we got negative 0.298 degrees C. Now that's the change in temperature of freezing. We haven't yet found the freezing temperature. That's what we need the other equation for. And the other equation is the change in temperature is equal to the final temperature minus the initial temperature. Yeah. Now what we set up here in our definitions earlier was that the initial temperature is always the freezing or boiling temperature of the pure solvent. So what we want for Ti is the freezing temperature for water. Yes? Yeah, the lowercase f is that's freezing, this is final. Freezing, final. Okay? So what's the freezing temperature of water in degrees C? 0. Our change in temperature we have right here. So we can plug in that number for change in temperature. Negative 0.298 degrees C equals temperature final is what we want to find, minus temperature initial, and temperature initial, you know, is 0.00 degrees C. Okay? So we just solve for TF. Now this is algebra stuff you've been doing since grade school, elementary school. How do you get TF by itself? Bingo. Add 0.00 degrees C to both sides. Plus 0.00 degrees C to this side, plus 0.00 degrees C to this side, and you get negative 0.298 degrees C equals temperature final. Yep. And there's your final answer. Yep. All right. Now you've got all the notes here, okay? To solve the homework problem I gave you, you need to go back and look at the notes and the problem solutions we gave you and just do the same thing. What? Where do you want to go to? Yeah. Yeah, you'll have to find the molality first. Class, I hope you were listening to the question and answer, because that really is a key thing for you to solve this problem, the homework problem. You've got to calculate molality before you can do this other stuff. Okay? The homework problem? Okay.
Wednesday and Friday I will not be here because of RTC.
Okay. What's going on for RTC?
Wednesday we've got like...
Oh, Wednesday and Friday. Okay.
Wednesday and Friday we've got like AFI, which is like an annual inspection. Yeah, major inspection. Then we have the best squad competition. So that takes up first and second.
Wow, that's a lot in 1 week, huh? Well, if you'll remind me, especially if you remind me by email the night before, I'll try to record the class for you if it'll help you.
Okay.
Okay?
Are there any other equation types we'll be starting?
This section is all about this. So the test we're going to do on probably Thursday, I hope to do it on Thursday, will all be just this stuff right here. Okay?
My kid would get here.